Good morning everyone. So, today I am going to start the first lecture of this lecture course series, that is on calculus of variations. As I have told in my introductory video that this course is primarily on the introduction to calculus of variations with specific applications in control theory and nanomechanics, which will be introduced towards the later half of this course. So, just to introduce all the students regarding what this branch is all about. So, calculus of variations, let me denote calculus of variations by this shorthand abbreviation COV. So, COV is concerned about the maximization or the minimization of functionals. So, as we move along the course, I am going to talk about what are functionals. So, functionals, just in layman's term, these are mappings from the set of functions to real numbers. From the set of functions to real numbers. Okay, so we will talk about so when we talk about calculus of variations, it is all about finding the maxima or minima, also known as the extrema of functions. So, the extremals in this case, these are not real numbers, but these are functions itself, right, as opposed to what is regularly taught in multivariate calculus, as opposed to vectors, in Rn or in finite dimensional calculus. So, with this very brief introduction, let me also talk about the history of this course. Right. So, calculus of variations has all along been with us since the 1800s. The early mention of this course, this topic, was done by the Bernoulli brothers, and I am going to over the discourse I am going to reveal some of the problems that were introduced by these mathematicians. Right, and then this course was also further introduced by several other mathematicians, including Leibniz, Euler, Lagrange and Legendre. So, as we go along this course, I am going to introduce several important results related to this course, which were introduced primarily by Euler and Lagrange. And towards the end, when we talk about the sufficient conditions for finding the extremals, there is a very vital contribution by Legendre. So, in the 1900s, more contribution came from Jacobi, from Weierstrass. We are going to introduce some set of other important results from Weierstrass as well as Jacobi over the later half of this course. In fact, in the International Congress of Mathematicians, it was Hilbert who introduced the famous 23 problems . The 23 problems in calculus of variations. And finally, in the 20th century, the contribution came from the likes of Hilbert, from the likes of Noethers. We are going to introduce a very vital result by Noether, as well as Tonelli, Lebesgue and finally Hadamard. well, so since then, you know, this topic has primarily found several applications, two of which we are going to introduce in this course. Now then let me also introduce some applications of this course. This course this topic is primarily applicable in the areas of mechanics, namely classical mechanics, starting from continuum mechanics as well as electrodynamics. And we will also see that some of the applications that arise in economics, namely in urban planning, and some of the other non-traditional areas. So, then a very vital application that we are going to introduce over the later half of this course is the application in control theory. And finally, we time over and over again during the different parts of this lecture series, I am going to introduce several applications in mathematics, which includes case studies in geometry and differential equations. So, these problems are widespread throughout the discourse of this lecture series. So, let me start with giving some classic examples, starting with the very simple case study. So, let me call this as case 0, right. So, let me introduce the topic of extremization of functional with the classic gold diggers problem, right. So, as the name suggests, the person who has to in this problem, there is a field, let us say there is a field that has lots of golds in patches. Let us say these patches, they represent gold, and the idea, the objective of the person who is digging the gold out of the field is to find a path such that he or she can collect the maximum amount of gold, right. So, the problem is as follows. So, we consider a field containing particles of gold, and the objective is to collect the most amount of gold by choosing the best path, right. So, we are given we have to, out of the family of different paths, we have to choose the best path so that we can collect the maximum amount of gold. And however, the problem that we have is that the total path length in this case is limited. So, whatever path we choose, we have to make sure that the total length of that path cannot exceed a certain value. So, in this problem we can see that we are maximizing a function of a function. So, what are we doing? We are collecting gold. So, gold is collected on the path, and that path is the integral of the gold at each point. Okay. And further I have mentioned that the length of the path is fixed. And so, we can see that we are maximizing an integral which is our path length, an integral over a path for all possible paths. That is, we are maximizing a function of a function. So, we can see that the integral over the path in this case is the integral of over a path in this case is the function, and the gold collected is another function. So, we are maximizing a function of a function, right, where this function is the amount of gold collected and this function is the integral over all possible paths that are available with fixed path length. Yes, so the second problem that I want to discuss is the problem of catenary that was originally introduced by the younger of the Bernoulli brothers, Jacob Bernoulli, in 1690. So, I am going to state the simplest version of this problem, and over the course of our lecture series I am going to show you the solution as well as the different variations of this problem. So, the simplest version is as follows. So, let us assume that we have two poles of different lengths. Let us say the first pole is of length y0 and the second pole is of length y1, and the two poles are separated by a distance d apart. Pole 1 has an x coordinate x naught and pole 2 has an x coordinate x 1, and between the two poles we have a rope which is hanging, so that the end points of the rope are fixed on the top of these two poles, and the shape of the rope is completely influenced by the action of gravity. So, it is completely weight which is determining the shape of the pole. So, the problem is as follows. The problem is, let us consider a thin, uniformly heavy flexible cable, uniformly heavy flexible cable suspended from the top of the two poles as I have shown in the figure, and the poles are of height y0 and y1 respectively as shown in the figure again, and these are spaced a distance of d apart. So, the problem says we have to figure out the optimal shape, of the cable between these two poles, right. Okay. So, now the problem says that we have to find the optimal shape. So, this question is, what is it that we are trying to optimize? It turns out that we are trying to optimize the total energy of the system, or we are trying to minimize the total energy of the system. So, as the cable is not moving, the total energy is just the potential energy. So, we see that the cable assumes a specific shape which makes the potential energy. So, I denote the potential energy by P e, which makes this potential energy the minimum, right. So, that is the governing factor of the shape of this cable. Now, further there are some simplifying assumptions. We assume, as the problem says, we assume homogeneous mass per unit length, and let us say that mass per unit length is given by m. So, the cable is a homogeneous cable, the mass is distributed homogeneously throughout the length of the cable, and then further the gravitational constant is denoted by G. So, in this case let us say our potential energy, let us denote it by W p. So, in this case my potential energy W p is denoted by the total summation or the total integral of mass times the gravitational constant times the height of the cable above the ground, and we see that we see that this particular integrating variable S is the arc length of the cable, right, and this particular variable Y is the height of the cable at S units along the length of the cable, right. Okay. Now, then further we assume that the length of the cable is fixed. So, in fact, this potential energy is integrated over the entire length of the cable, integral 0 to L, and the simplest version of this problem we assume that this length, although it is fixed, but it is an unknown in the problem, right. Okay. Now, so this is the original, we see that this particular, let me denote it by 1. So, 1 denotes an integral of a function. So, y is the height function and W p is the function or the integral of a function, and hence W p, the potential energy, is a functional. So, we can then the next step of this problem is to recast this particular problem denoted by this 1 in a simpler form. So, we recast 1 in the Cartesian coordinates. Let us say that, let us say my x coordinate is along this direction and my y coordinate is along this direction. So, we recast our problem in the Cartesian coordinates using the fact that the length element ds is the square root of dx square plus dy square. So, simple Pythagoras theorem, or this can also be recasted as follows. This is 1 plus dy by dx square times dx, right, or this is also equal to the integral of the square root of 1 plus y prime. So, when I say prime, this is the derivative with respect to x. So, y prime square times dx. So, that is my arc length in terms of the height and the x coordinate of the system. So, finally, my potential energy now can be recast into the Cartesian variables. So, we have in terms of x, my endpoints in the x coordinate are x 0 and x 1, and my new functional is m g y of x times d s, which is given by 1 plus y prime square d x. Okay. So, let us denote this new functional by 1 prime, and we see that the unknown of the problem, or what we are trying to optimize is, or find the optimal solution is the solution to this y of x, which is the height of the cable at a distance x. So, we assume, one assumption in this optimization problem is, we assume that the solution to 1 prime, the solution y of x is continuous and piecewise differentiable at the barest minimum, right. And then further we can ignore some of the constants in the problem. We can ignore constants like m g. So, this is just a constant in the setup, and we can take it equal to 1 or ignore it, right. And in that case, the new functional in this catenary problem reduces to the following functional. Let us denote this new functional by j of y, which is integral from x 0 to x 1 y of x square root of 1 plus y prime square dx. Let me denote it by this new number 1 double prime, and further this optimization is for fixed boundary conditions. So, from now on I am going to denote my boundary condition with this short notation b dot c. My boundary conditions are y of x naught is y naught and y at x 1 is y 1. So, this is the case of a fixed boundary condition problem. A similar and a more general version of this catenary problem is the problem of catenoid. So, what is the problem of catenoid? So, let us again go back to our diagram of catenary. We have this rope which is hanging between the two cables y 0 to y 1, and further suppose we are able to rotate this cable along this x axis, right. So, we can see that it is going to generate a surface of revolution about the axis of rotation x, and this particular surface that I am talking about, this particular surface is the catenoid. So, this is my catenoid. Okay. So, catenoid is the surface of revolution. Catenoid is the surface of revolution with minimum area. Catenoid is the surface of revolution with minimum area that is generated by revolving the catenary, right. So, in this case the extremal, we want to find the extremal of the following functional j of y, which is this is my area functional. So, we are trying to minimize the area of the surface of revolution. So, the area, right. So, we are trying to minimize this area, and the area could be is given by the integral x 0 to x 1. So, this is my point x 0 and this is my point x 1, and so the area is given by the area of this irregular cylinder, which is 2 pi times y, absolute value of y, which is the height, the absolute value of y is the height of this catenary times ds, which is the lateral length of this cable or the arc length. Okay. So, moving along, one major assumption in the catenary problem is that we have to assume certain constraints on the length of the cable, right. The length of the cable L has to be greater than or equal to the distance between the 2 points, sorry. The length of the cable has to be greater than or equal to the distance between the 2 points, because if L is equal to this particular square root distance, we see that the solution to the catenary problem is just a straight line, gives straight line as solution. Okay. So, then a modified version of this problem is we can assume that the length which is given by the integral of this arc length or this following integral